So in this talk, I'm going to try to go over some of the many caching options that are available to you in Python, Django, and with OpenNetX utilities. Caching is extremely important to backend performance. We use it all over the platform, but sometimes it's a little hard to know what to use when and what tools are available. So quick agenda, we'll go over some definitions, motivations, drawbacks. We'll compare the different options of the different layers, go over some operational issues that you might run into, and then some design considerations for how you can actually design for caching. So, quick definition, what is backend caching and what do I mean by it? So I'm talking right now specifically about Python and Django layer caching. This is not browser and CDN. That is a fascinating subject, which would be a talk entirely of its own. Most of our caching that we use in our services is read-through caching, meaning that we look for a value in the cache. When we are serving a request, if we don't see that value, we do some recalculation, we stuff that value back into the cache, and then we continue serving the request. Some of our caching is write-through. This means that we put stuff into the cache as soon as we do the writing because we know other things are going to need it later. This happens particularly when when it's really expensive, if it takes a long time to do the computation. Caches are ephemeral. This is in bold because if you assume that cache values will stick around, there is a world of operational pain waiting for you. The program's cache is an example of this for anyone who's had to deal with that. And so by ephemeral, it means that a cache miss should not affect the correctness of your application. Cache misses make your application slower because they don't have access to that pre-computed data, but they don't actually change the behavior and the answers it'll give. And for the purposes of this presentation, data replication is not caching. So data replication, what I mean by that is when we take data from one service or one particular set of applications, we do some sort of transformation and we copy it either to another service or another application, store it in the database. We do that a lot of places, but that for the purposes of this talk, that is not covered in caching. All right, why do we love caching? Makes our apps faster. The users love that. If our apps are faster, it takes less hardware to serve them. That reduces our costs. That's great. But these aren't really why we love caching. These are nice. But the real reason is because it's easy, right? It's low effort and low risk. Caching is the duct tape of the performance world. It's the first thing you turn to. And what are the drawbacks? So when we add caching, we're essentially adding global state. And this can often make code and testing more complex and harder to reason about. The behavior of your services becomes less predictable because you can have a service that was nice and zippy and fine, and then the cache expires or something, and then suddenly it takes 10 times as long, and you're not expecting that as a consumer. And they can cause memory leaks, and they can cause memory leaks in a way that is difficult to diagnose. But now into the fun stuff. Now that we have the disclaimer out, Python caching. So in here, the functools package in the standard library is your best friend. So the first thing we're going to look at is something called cache property. For those who are familiar with Python's property decorator, it does basically the exact same thing, except it caches the result, so it only calls the underlying method once. So what happens is if you put cache property over one of your methods, you can call it as if it was an attribute. The first time it's called, it'll do the expensive computation, actually run the method. All subsequent times, it'll just go and use the cache value. Now, there's nothing particularly magical about that. You can't do the equivalent thing in your own code. So here we have the underscore verified mode is our cache variable. And we initialize it to none in the constructor. And then we check if it's none in this get verified mode method that we have. And if it's still in an uncached state, we do the hard work, and then we return the cache variable. That sort of setup works fine when none, the value none is not a valid value to return from that method. And it's sort of idiomatic Python when none is not a valid return value. But When you do have to return none, you can use what's called a sentinel value. And so here we set a sentinel, verified mode sentinel, and we just assign it an object. The only purpose of that sentinel is that it will not compare to be equal to anything else. So you can use it to signify a cache miss. And so you check, instead of checking if self-verified mode is none, you check if the self-verified mode is equal to the sentinel, and then it's the same sort of logic. So you might also ask, like, why would you do this, right? Like, what's the difference between the thing on the left and the thing on the right? And why would you make your own methods and cache them when you can use Python magic and just have it done for you? So this is one of my personal rants is you should not hide data access, remote data access, because it is a different thing. Code is as much about communicating your intent to your fellow developers as it is about telling the computer what to do. And so when I look at the thing on the left, I think this is just an attribute. We're fine. This is going to be fast. There are no errors that are going to happen. There's no network timeout. When I see a thing on the right, I think, like, things can happen. Like, a work is actually being done here. So this is just my personal take. But yeah. So shifting over, we're going to do a quick case study on theming and Docker. So this is something EduNext ran into. They found that adding 4 themes could triple the response times of certain views. And this is because a function called isThemeDir was invoked thousands of times per view, and each time it was being invoked, it did file system access. Now, file system access is slow. Operating systems know it's slow, and so they will use gobs and gobs of RAM in what's called a page cache in order to make sure that they can serve that data quickly, so you don't actually have to hit the disk. But for some reason, this was working in the VMs, and it was not working in the Docker when it was deployed in Docker. So then, their face is like the choice of what do we do at this point? You can refactor this so that it does the work on startup initialization. How do we handle this? Well, this was the function in question, or one of the 2 functions in question. And you see the slow file I/O on the bottom. It's calling listdir, and isThemeDir was calling like isdir. So one thing we notice is we can't use cache property on this. This is not a method on an object. It's a function. Also, it takes an argument, or an optional argument at least. And so when picking the caching solution for theming, the constraints we have is there's no expiration or invalidation. Right? Themes are good for the lifetime of the process. They don't change. There's small size. There are few values. Those functions are only called with one argument. That's usually the same argument. So a very small size. But the latency is critical. It has to be really fast. We can't go out to like another server to get those cache values. And so this is almost a textbook use case for LRU cache, which is also in the functools package. So LRU stands for least recently used. That is the eviction policy, meaning that once the cache fills up, if you try to add a new thing into the cache, it will kick out the least recently used item in your cache. So this is great for this use case. The no expiration and validation is great because you can only clear the LRU cache. You actually can't invalidate individual keys in an LRU cache, at least when you use the decorator. Small size, few values, that's great because an LRU cache is almost an invitation to memory leaks, and so having something small is good. And the low latency, this is as fast as you're going to get. It's part of the standard library. It's got some C stuff underneath. It's fast. And using the LRU cache is just that. Right? You import it, and then boom, you slap it on, and the magic happens. Using it in tests is a little more complicated. So when you actually put the decorator onto your functions, what happens is that your functions are objects. And the LRU cache decorator sticks a method onto those objects for clearing the cache. And so in your setup in Teardown, you actually have to import these functions into your tests and clear them explicitly. And the results are phenomenal. Right? The median load time went from 3.56 seconds to 607 milliseconds. This is 20 lines of code did this, and actually 4 lines of code and some tests, right? And I don't want to sort of undercount the effort that went into this. like a lot of performance work, the vast majority of the effort was in the analysis and the testing, setting up the load tests, running the profiler, digging through the profiler results. But this little thing at the end is nice because it is low risk. Again, right? We just patch it a little bit and we did magic. So that was the LRU cache. Now on to the Django and its cache framework. Okay, so the Django cache framework in a nutshell. The low-level framework, we have get, set, delete. We can do this. They have get many, set many when you know you're doing a bunch of keys in parallel. And then we have some things that are view-level caches that honestly we don't use as much, mostly because most of our caching is centered around API calls, and we do per user checks on those for access and so forth. It also supports multiple caches and multiple cache backends. Though usually this is just Redis or Memcache. For our cases, it's Redis in any tutor-based install, but orgs like edX, like 2U, still uses Memcache. So now, so we go to the first thing that you have to be careful of. With Memcache, because of the limitation in the current Memcache library that we use for most of our services and for our edX platform, if you try to insert none as a value to the cache and try to fetch it back, it will come across as a cache miss. This is the way you're supposed to use the Django Cache API to do a get to differentiate between sort of a none value and a cache miss. You create a sentinel, just like we did in our previous example, and you call cache.get with your key, and you pass in the sentinel as the default value. If you get the sentinel back, that means there was a cache miss. The thing that will happen in Memcache today is if you try this, you try to get you do this with a text key, or you do this and there's no value, you get the cache miss like you expect. Then you insert a string, and then you get the cache value. It does exactly what it's supposed to. It returns the string that you inserted. Then you insert none, and you say get with the sentinel, and then it returns you the sentinel. So this is not something that affects Redis. If you develop or deploy on Tutor, this is not going to affect you, but your code is deployed by people who run Memcache, so this will still bite. So in any case, this does get better. In the Quince release, we are going to upgrade to Django 4.2. That will involve changing the Memcache backend. So this should go away as of Quince, but as of Palm, this is still a problem. Another issue you might come across is that cache invalidation is hard. It's really annoying. Figuring out when you're going to expire data, figuring out how long, is it okay to cache this for 10 minutes, for 5 minutes? How long do I deal with stale data? Is it okay? Also, if you have a lot of keys that you have to actually explicitly clean up, because say you are, lazily instantiating the key, the cache values at the time of the request, but then you have to clean up all the old ones when a certain action happens. Because it starts out innocent enough. You have one key, and then you have ×4 times the types of users you have, and then ×8 by the types of institutions, and then it starts blowing out. You can also have cleanup failures that happen if whatever is supposed to clean up your keys entries at the end errors for some reason. You can get into this weird state where you have stale data hanging around. And you can get race conditions. This doesn't happen often, but if you're running at scale, say you are serving some course information, serving some information about a course, and the course publishes, the publish finishes in between the time you start serving that request and the time you stop serving that request. You can get kind of mixed cache information from two different versions of the course. Again, doesn't happen often, but it does happen. And one of the things you can do to mitigate this is to actually create new keys instead. So instead of, in this case, you have the course key, a course outline with a course key, you can add version information to that course key. And this actually solves a lot of the problems. So when to expire? You never expire it. And this is sort of a deeper thing, right? When you think is that the contents of a course changes over time. The truth of that changes. The contents of a course at a specific version of that course is forever. Like, it's always good. The reason you have to delete cache entries and you have to clean up after yourself is if those cache entries are wrong, if they no longer reflect the truth. But if you tie it to something like a version ID, then those cache entries always stay true. And the key growth, like, yeah, you make lots and lots of keys in this scenario, and you forget about them. You never have to clean up after them. Because Memcache and Redis will both kick out the old keys for you, so you don't really have to worry about that. And race conditions, like the versions are isolated, so you don't get into those in-between states. You're always talking about one specific version of the course. You don't have to worry if there's a weird publish in between, because even if there's a new version, you're still talking about the old version. But wait, I'm going through this very quickly. Where does the version come from, right? Like, where do we put this? So here's one thing I think trips up a lot of people when they start caching, okay? And I want to reiterate this. Memcache and Redis is not free, and the database is not lava. You can touch the database. A lot of people feel that when they first get into caching, there is this sort of intuition that the cache is fast, the database is slow, and we should try to avoid the database as much as possible. That's only partially correct, right? So the 1 millisecond is roughly, very roughly, that's about how long it takes to do a fetch in AWS Memcache to do a cache fetch. It's about a millisecond. That's also about the same amount of time if you are doing a simple query with little data for one row in a well-indexed table in your database. That's about how long it takes. So this means that we can work together. It's not always an either or, right? So this is the course outline. And this is the work done by the Learning Sequences API in order to get the course outline that not customized to an individual user, but the course outline as a whole. And you see it's like 6 models. Maybe it returns 100 rows. There are a bunch of joins and all of that. And maybe that takes 50 milliseconds to pull from the database, run through ORM, all of that. On the right side, we can sort of synthesize that into one cache entry and slap it into Memcache or Redis in like a 1 millisecond pull operation. So 50 versus 1, okay, maybe I'll go and I'll cache it, but then how long do I cache it for? Like 1 minute, 2 minutes? How long am I willing to let it be stale? But if I just do a 1 millisecond lookup row to actually see what the currently published version is, and I use that to decide like where my cache key is and what to fetch from the cache, then I go from like it's to 2 milliseconds instead of 50, right? Or instead of 1 or 50, it's 2. And that's a good trade-off. Like, it means you spend just a little bit extra time to do the work, but then you are guaranteed that you never have stale results. And databases and caches should work together like this, right? So the one example we have is the old programs cache. The programs cache is actually much more complicated now, but I'll just start with like in the very beginning, it was basically a mapping of programs to course runs that lived in Memcache. And this worked fine when we had one program with 4 courses in it. It did not work well when we started scaling and there were hundreds of courses and programs and so forth. It actually got to the point where it took, I think it started to take almost like a full second of the page load or the student dashboard at one point to just pull this gigantic thing from the cache. So this is my other really important point. Do not use cache entries as a database. If you have to do searches, joins, anything like that, no amount of sometimes this comes again from this false intuition that the cache is going to be faster, is always going to be faster. Sometimes this comes because you have a dirty hack that you've lost track of, and then you put a quick hack for 4 courses, and then you grew to 4,000 courses, and no one noticed. How you can go and how you can find when you are starting to do this is if your application has these big cache entries, and then you start pulling back these huge cache entries to pick 1 or 2 items and join them together in application code and to make relationships, then you are on this path and you need to step off it or there is pain awaiting you. So yeah, caches and database work really well together. So don't think you have to go completely off of databases. Few odds and ends. There is a Django local memory cache backend. This is It's very fast. It's in process. You call it like a normal Django Cache API, but it's just hitting something that's like in memory. Unlike the LRU cache, you can expire entries, but you still have memory leaks. It doesn't actually, the expired entries don't actually disappear from the cache until you access them. So if you have a bunch of old keys, they just keep accumulating. Which makes it surprisingly less useful than it sounds. But if you have something where you have a very limited number of entries that are going to be for the lifetime of the process, but they can possibly expire, that it is a good option to try. Finally, we'll get to the OpenEdX caching utilities. Here's special thanks to Robert Raposa and Chris Lee from TU and edX. So Robert Raposa is actually, they wrote this years ago. Robert is still with TU, and actually he will be giving a talk tomorrow on the event bus, which I encourage you all to go to. And one thing to start with, a data point, is that Memcache Redis caching, the latency is about 10,000 times slower than the in-process caching that you can do with LRU cache and the like. It's the difference between about 1 millisecond and about 100 nanoseconds, give or take. So here's the case study. Here's coarse waffle flags. For those not familiar, coarse waffle flags are basically feature toggles that we have in platform. They can be customized for, they can be overridden for a specific organization or a specific course within that organization. And that means there are a very large number of potential keys, because the number of courses, which can be thousands of courses, multiplied by the number of features. And so, Django local memory cache leaks memory. Maybe this isn't the best fit to hold this. The frequency is hundreds of lookups per request. So this makes Memcache and Redis, it takes it off the table, because that's too slow. You don't want to spend half your request time just talking to the cache. The lifetime of these we want fresh values to come in less than a minute. If someone changes a toggle, one of these toggles, they want to see the result ideally immediately, but probably no more than a minute from when they flip the switch. If it was an LRU cache, it would just live on to the end of the process, which could be many minutes. So for this, we use request cache. I think it might have actually been developed for this use case. I'm not sure. But in any case, this is an in-memory cache that is cleared at the end of every request. And so to use this, you have to include this middleware. And this is the way they use it. So you have, you declare a request cache, you give it a specific namespace, you say get cache response with a particular, with your cache key, and then if it's found, you do something with the value attribute. You might have noticed there's some overlap with the way request cache and cache property work. So one thing you might consider if you're considering the two options is that for cache property, say you have a view function, and it calls a function, this calls a for loop, there are like 5 functions down, and way down at the bottom is some cache access. If you use cache property, you would have to pass that object all the way down the stack in order to get it. And so for these cases, you don't. You use request cache. You do the simple thing. And request cache is essentially a global that lives for the lifetime of the request. You might also ask, can I use Memcache and Redis together with request cache? And the answer is yes. In fact, this was such a common use case that they created tiered cache to do exactly this. So tiered cache looks a lot like the API for request cache, except you don't get your own namespace because you have you just have a long cache key and when you do the get, first it's going to check to see the local request cache to see if it's already been fetched. If it's not in the local request cache, it'll go out to Memcache to look for that key. So tiered cache is trying to have the best of both worlds, where you can access it 100 times very quickly within the same request because it's going to do the local lookup in the request cache, but you can still share that cache value across multiple requests. All right, side note, cache misses and falsy values. So I mentioned before how when you use the cache.get of the Django API, you should send in a sentinel, especially if you care about none types as possible values. Sometimes we see code like this, where you just where you do like if not cache value on the return and assume that means the cache miss, and it's not, right? Like this will happen if you store an empty list. This will happen if you store a 0. This will happen if you store false. So just a thing to be aware of. This is actually why cached response, the things that return from the request cache and tier cache, is built the way it is to force the developer to explicitly say, like, is found is different from the actual value that's returned. Also, the cache response, the other thing to note is that it does suffer from the same underlying memcache issue, where if you save none into memcache, you will get a cache miss when you're trying to pull it back. Request cache doesn't suffer from that issue, so you'll get a miss on the memcache on the outside, but the request cache will do the right thing and cache it properly. You can force cache miss with the tier cache if you add this middleware. There are more details about this in the docs, just for a debugging tool. The other thing is testing. There's a cache isolation test case. It is in edX platform. It should be in edX Django utils. But basically, this resets both the request cache and the Django caches between test runs, so you don't have to worry about it. If someone is interested in actually moving it to edX Django utils, please come talk to me after this talk. And when you are doing your testing, you want to test that your cache actually works. So we use assert num queries a lot in order to do this sort of testing. You can do query counts. Try to do the query counts only in your API.py files, test files, not at your view layer. At your view layer, you're going to get a lot of other stuff that's going to interfere. So you want to try to test as little as possible. And when you write it, please put comments saying what's going on, because there's very little more confusing than looking at 2 consecutive calls 5 years later and just seeing the query counts different and wondering what's going on. All right, so quick review, deciding on caching strategy. All right, so we start with the number of calls per request. If it's only one call or a few calls, we can go and use the Django Cache API, memcache Redis. It's fast enough. Everyone will be familiar with it because it's a standard Django thing. If it has if it's called many times during the same request, then we can look at the lifetime of the value. If it's called many times in sub-requests and the lifetime of the value is the entire life of the process, meaning it never gets invalidated, then we can use, anyone, shout out? No, request cache is just the life of that's just the life of the request. If I would do LRU cache, yes, LRU cache. So, but if the lifetime of the value is for the request and the access pattern is very simple, then we can use the cache property. But if it is deeply nested, but it has to live for the lifetime of the request, then we use request cache. Absolutely. Popping back up, if the lifetime of the value is across multiple requests and the number of values is very small, then we can use the Django Cache API with local memory. But if it has to last across multiple requests, it has to be very fast, and it has to be, there are many, many potential values. We can use, anyone? Tiered cache, yes. Great. Awesome. All right, so now operational issues. These are things that will bite you in the middle of the night. All right, first thing, memcache's default is 1 megabyte for its value limit. Set this to 2 megabytes, just because this, particularly if you have large courses. Second, memcache versions silent failures. Get or set will silently fail if it can't reach the cache, whether it's Redis or memcache. It will not throw errors. It will not give you helpful logging. It will just fail. It'll do a cache miss each time. So this can be either misconfiguration or server failure. When the server comes back up, if it's Redis, it will reconnect almost immediately. If it's memcache, it can stay dead for, like, the Django won't see it for about a full minute or so. There's also something called a cache stampede or dogpiling. So normally when there is a cache miss, like you're running most of your unicorn workers or web workers are getting cache hits. One is getting a cache miss, and oh, that's fine. It's recomputing, whatever. If all the cache entries die at once, all the unicorn workers are hitting the cache miss. They're all trying to recompute things. Then suddenly you see this huge spike in latency, and your throughput tanks. There's terrible waves in your monitoring, and a world of pain, again, paging you at night. So the only real solution that we've sort of done for handle cache stampede is to actually replicate data out. So what happens right now, let's say you have a unicorn worker, and on the cache miss, it has to recompute some values, and it's really expensive. It calls an external service, crazy data models, S3, to serve the request. So when you replicate the data, instead you have a celery worker that does all that work, and then it sticks it into a much simpler data model. So when your web request does that cache miss, it will just read off the simple data model, and then you don't get that stampede effect. This is operationally more complicated, but this will give you much smoother performance for your users. The other issue is load balancing course-based cache keys. A number of your cache keys, if they are based on the course, that means that all of that course's cache entries are going to one place. So this happens, for instance, for the structure document, can happen for a structure document caches. But say you have, so like your first cache entry goes into shard 1 of your cluster, the second one goes down here, third one goes up here. But then you have one course that's this giant whale of a course. It's bigger than all your other courses, and it's like 75% of your traffic on your course. You can have it so that you can find yourself in a situation where 2/3 of your cluster is doing nothing, and 1/3 is taxed, and the only way you can fix it is to upgrade your entire cluster. So one of the things that we talked about but never implemented, so this has a question mark at the end, is if we can actually add a small random element to the end of the cache keys to force the distribution of it. This uses more space. Essentially, we'll be making like 10 times the cache keys potentially for a few limited cache keys. But then that would spread around the CPU load so that it would be like, and CPU has always been what has gated the platform on cache more so than space traditionally. And finally, designing, in terms of designing for caching, because it doesn't always have to be duct tape. Keep in mind, when you're building your programs to be, that when things go wrong, someone else is going to come in. One of the first things they're going to do is they're going to try to ask, how do you cache? Like, can I cache this? Is this safe to cache? I don't understand this person's code, but like maybe can I just tweak it here and fix it and go, and like, where do I put my duct tape? And when you have getHTML, like a method like this, problem block getHTML, you know that getHTML is a product of, like, there's some set of input states, right? The authored content, the user state, whatever feature flags. And, whatever problem block decides to do with that, run a sandbox Python code, do network, who knows what it's going to do. And from the outside, this makes it really difficult to cache. And one of the things I would encourage you to think about when you're thinking about your applications and your programs is to think about your data and think about it in terms of data transformations and not just objects and methods on those objects. So, you have a rendered problem block, but an author wrote some content in Studio. That is one thing, at least, that is shared across all these problem blocks. Is someone wrote authored that problem. And then it's combined with user state and then crazy logic, and that makes the rendered problem block. When you think about the course outline for a given student, you can think about, like, we take all courses, sections, and subsections, like the raw content, like that's shared across all users of the platform. And then we can say, like, maybe there is a set of track-specific data. And that is another element. Like, those things can be cached. Those things whatever we can share across those users in stages. And it makes it much easier. When you start to divide up your data like this, it makes it much easier to apply caching methods. Another thing is to manage your remote data access. This pattern happens a lot. where you have a view, there's some for loop somewhere, and some loop, and then way down in there, you have the same thing asking for a cache key 1 over here, and then the next cycle through the loop, there's cache key 2. And the thing is, like, the things at the bottom there have a very limited view of the world. Like, they don't know all the things that they're going to be asked for. But way up here, you actually know what's going on. You know that this person is in this course, and they have, like, you know, they might need these pieces of content. So looking at the, like, a very simplified version of the, like, course waffle flag situation. So we have 3 types of the course waffle flags here. And we'll have, like, one style we'll call it, like, for features. The second one for org level overrides of feature flags, and then the third one for, like, course level overrides of feature flags. And then you can imagine each time through the loop, different parts of it are asking for those 3 keys over and over again for, you know, however many features you have. But at the very beginning, fundamentally, you know that there are these 3 things that the course waffle flags will care about. You can actually, like, you could preload that cache, right? You could say at the very beginning, hey, you know, for this org, this course, like, just prefetch me all the values that I will care about. Do it in one place, and, you know, and have that available in your request cache for everything else to use. So yeah, so I guess the final thing I'll leave with is just please don't be afraid to explicitly model your data access. It doesn't make you a worse object-oriented programmer in order to admit that your data is actually on a separate server and it takes more time to go there. Like, there's a lot of, I feel like a lot of object-oriented literature tries to hide that, but it kind of conflates hiding the specific implementation of how that fetch happens, which I think is good. Like, you shouldn't have to say, like, you shouldn't have those details popping out. But the fact that you are doing an operation that is 10,000 times more expensive than pulling something locally means that you're allowed to actually express that in your code and sort of consolidate that data access. And actually, I was rushing through a lot of that because in every practice I did, I went over time, but I actually am not over time. So, all right. Any questions?
To take questions, I'll ask that you just raise your hand, and I'll pass the mic over to you.
Can you go to the slide where you were showing the flow chart of the, this one?
I totally did not expect questions on this one.
Well, I was just wondering about this Django cache API with local memory. Mm-hmm. If it's a value for multiple requests and it's stored in local memory, isn't it likely the next request is going to a different worker and then it won't see that cache value?
Yeah, so a lot of times, so Django uses, I think, this for things like template caching and so forth. So it will get recalculated, just like the LRU cache. It will get calculated per process. So this is something you wouldn't use for user information. Like, it's not like this user had this thing. You would use it for, like, almost always system level stuff, like the theme. Like, we could have done the themes directory there, and it would have worked fine. Anybody else? Wow, really? Okay. I'm sure that, like, some of my talk was too confusing and blurred. So, okay. Well, then, thank you very much. I will let you get to all your things. Oh, I forgot to, did I mention that the memcache thing will be fixed in Quince? Yes, great. Okay, I just wanted to get that. Do I have any volunteers to port the test utilities from edX platform to edX Django utils? Yeah, you can't blame me for trying, right? All right. Yes, sir.
On the third to last slide or something, what was the advantage to prefetching that cache stuff rather than letting it get fetched?
If you can repeat the question.
Oh, yes. Thank you. So the advantage of prefetching it up at the top instead of going down below is that when you get it down below, there are a series of separate fetches that each have to go to potentially to memcache to get that value, or to a database. Whereas if you prefetch it, you can do one query, and you could like fetch it out of the database, and you can get all the query of everything that could possibly affect the user, and you could do it once in one query, or you could do like 3 separate things for like the global ones, the like org specific ones, and the course specific ones. A lot of times you just know more at the top. There was one thing with video metadata information where at XVal was trying to look up video metadata, but it didn't know what videos were in like the particular subsection being rendered. And so it needed to constantly fetch that information over and over again. All right, thank you so much for coming. Oh, Jeremy.
I was going to say, if you haven't already done so, please add an issue for moving that code in the edX Django utils GitHub issues tracker. So,
Okay.
So that the team owning it can potentially prioritize that.
I will absolutely do so. Thank you.